Probability theory is the foundation of Monte Carlo simulation. It helps us understand and model uncertainty in the real world. What is a random variable? A random variable is a numerical outcome of a random event. There are two types: discrete random variables, which take specific values like rolling a die or flipping a coin. Continuous random variables, which can take any value within a range, like measuring temperature or stock prices. For example, if we roll a fair six-sided die, the number we get is a discrete random variable because there are only 6 possible values. But if we measure the exact height of a person, it's a continuous random variable because height can take an infinite number of values. Probability distributions. Each random variable follows a probability distribution, which tells us how likely different outcomes are. Some common distributions include uniform distribution, where every outcome is equally likely. Rolling a fair die is an example. Normal distribution, also called the bell curve, which appears in nature and finance. Most values cluster around the average, with fewer at the extremes. Binomial distribution, used when there are repeated independent trials with 2 possible outcomes, like flipping a coin multiple times. Poisson distribution, used for modeling rare events over a fixed period, such as the number of customers arriving at a store per hour. Understanding expected value. One important concept in probability is expected value. This tells us the average outcome we can expect over many repetitions of an event. For example, imagine a simple game where you either win or lose money. If you win, you get $10, and if you lose $5. If the chance of winning is equal to the chance of losing, then over many games, the average amount you make per play will balance out to a predictable number. Expected value helps us understand long-term outcomes and is widely used in decision-making, from business investments to casino games. Why probability is important for Monte Carlo simulations. Monte Carlo simulations rely on probability to generate random samples from a distribution and estimate complex outcomes. The more samples we take, the closer we get to the real-world behavior of a system. For example, in finance, Monte Carlo methods simulate thousands of possible future stock price movements to help investors estimate risk and return. In physics, they model how particles behave in nuclear reactions. By understanding probability distributions and expected values, we can make better predictions in uncertain environments. This is the power behind Monte Carlo methods.